All right, we good so far? It's pretty much the last section, redox reactions, which again is chemistry, but it's bridging chemistry and biology together. Right? ATP is all biology. You need to know how we got into it. So we have these things called redox reactions. The redox is kind of, not an acronym, it's kind of a two-word combination. Something reduced and something's oxidized. So we call them redox reactions. It transfers electrons between reactants. And this releases energy that was somehow stored in an organic substance. And this energy can be used to make ATP. We can have an oxidation reaction and a reduction reaction. Thus, these fall under the umbrella of redox reactions. If a substance loses electrons, we say that it's been oxidized. Okay? So it loses electrons. Does it become positive or negative? Positive. Is it a cation or an anion? Cation. See, we're going backwards to some stuff we talked about a couple months ago. A couple weeks ago. Okay? But oxidation is when the substance loses electrons. It's said to be oxidized. Reduction is a substance that gains electrons. Because an electron has a negative charge. If it goes onto something, does that something become an anion or a cation? Anion, right? So then we say that it's reduced. The amount of positive charge has been reduced. So when you do something like this, sodium becomes oxidized when this goes in water, and chloride becomes reduced. Right? Becomes negative, an anion. So that was an easy one to show, but there's other ones on there too. They, just use it like a algebra equation. If you're going to be oxidized, you're going to gain the electron, and it becomes reduced, you're going to, if it becomes oxidized, you lose the electron. If you get reduced, you gain the electron. The little mnemonic that I've used when I was in college was Leo Ger. Leo loses electrons, it's oxidation. Gers, G-E-R, right? Gain electron, a reduction reaction happens. Okay? Now, the nomenclature here gets a little confusing. Because now we've got to deal with something called a reducing agent. A reducing agent gets oxidized because it's making something lose an electron. All right? So this is going to donate an electron. So therefore, it's going to, the reducing agent gets oxidized. As opposed to an oxidizing agent, the electron acceptor, the oxidizing agent gets reduced. Hint, hint, understand this. I guarantee there'll be a question on the exam next week. Understanding these terms, Leo Gers and oxidizing agents and stuff. Make sure you know that. We'll be using those terms when we get into tomorrow's lecture. Okay? So in cellular respiration, glucose gets oxidized, but oxygen gets reduced. To give you an idea of what we're going to be dealing with. So here's glucose. Here's oxygen. Glucose becomes oxidized into carbon dioxide. O2 gets reduced to water. We get energy.
A reduction-oxidation redox reaction always involves two events. One substance loses electrons and is said to be oxidized, while another substance gains electrons and is said to be reduced. Sodium chloride, or table salt, offers an example of atoms that have undergone oxidation and reduction to become ions. When sodium and chlorine react to form sodium chloride, one electron is completely transferred from the sodium atom to the chlorine atom. The result is a sodium cation and a chloride anion. In this redox reaction, the sodium atom lost an electron. It was oxidized. The new sodium ion is a positively charged cation. The chlorine atom gained an electron. It was reduced. The new chloride ion is a negatively charged anion. In redox reactions, electrons can be transferred completely from one molecule or atom to another, forming an ionic bond, or they can simply shift positions in covalent bonds. The combustion of methane is a good example of this second type of reaction. The electrons in the two reactants, methane and oxygen, are shown as dots at equal distance from the atom's nuclei, indicating that electrons are shared equally. When electrons are shared equally, the bonds are nonpolar. Methane combustion involves the reaction of two oxygen molecules with each methane molecule. The reaction yields carbon dioxide and water as the products. The atoms in the products share electrons unequally, meaning that the bonds are polar. In carbon dioxide, the nucleus of the carbon atom holds the electrons less tightly. Carbon has been oxidized. It lost electrons. In water, the nucleus of the oxygen atom holds the electrons more tightly. Oxygen has been reduced. It gained electrons. Because the atomic nuclei of the product molecules hold the electrons more tightly than they were held in the reactant molecules, the products have lower potential energy. Such reactions tend to be spontaneous or exergonic and release free energy.
Now, cellular respiration. Cellular respiration includes both aerobic and anaerobic respiration, which means aerobic means we use oxygen, anaerobic means we don't use oxygen. We can make ATP without oxygen. Really? Yes. Not that well, though. We can't live with no oxygen for very long. Try and hold your breath. Okay? But we can. So this includes aerobic and anaerobic respiration. But when we talk about cellular respiration, most cases we refer to the anaerobic respiration only. Although we use all those biological macromolecules, namely the sugars, the fats, and the proteins, they're going to be used as energy, as fuel to make this energy. It's helpful to trace how the cellular respiration actually uses the glucose molecule, and we break it up. This is a very important reaction you need to know. Hint, hint, I may ask you this. Cellular respiration is going from glucose and taking glucose and oxygen and making carbon dioxide and water, and you're going to get energy. That's cellular respiration. We can can do the opposite. Not we, but certain organisms can do the opposite, where it's going to take carbon dioxide from the air and water from the soil. Energy needs to come in, and it could go this way to make glucose. Who does that? Plants. And what I just explained to you was photosynthesis. They need to make their sugar, and then from this sugar and oxygen, they can actually create their own energy. But in order from going from simpler to more the oxygen. But in order from going from simpler to more complex, you need to put energy into this system. Where do plants get its energy? Sunlight. So cellular respiration is this way. Photosynthesis is the other way. You do know that reaction. So we have a lot of redox reactions happening in cellular respiration. Glucose and other organic molecules are broken down in a series of steps. There's something called NAD+, and this is where electrons from organic compounds are usually transferred to this coenzyme. And this coenzyme is going to carry those electrons to another process, to another factory, so that it can actually turn that into ATP. It functions as an oxidation agent, i.e. an electron acceptor, and when it does, the NAD+ gets reduced and is now called NADH. It just accepted that hydrogen ion, that electron. And now this is stored energy. It's got an electron that can power and make ATP. So this is the reduced form, that's the oxidized form. And we're going to be doing that all up on the board here tomorrow. So the H comes off of this, goes onto this to create heat. Worry too much now, but it's trying to show you from the NAD where the electrons come off and go back onto the ADP and create an ADH. That can be used to make ATP. In order to do this, we've got to learn another process still within cellular respiration, called the electron transport chain. It's transporting that electron that the NAD has, or the NADH has, and transferring it on a number of different structures to eventually make that ATP. It's a chain of events that happen. So NADH and FADH2 passes these electrons through this chain, this electron transport chain. And in order to do that, it has to do it as a chain. It does it in steps. Like you could jump from the top of the steps, which is 6 steps. You could jump from there all the way down to the floor, but this reaction doesn't work that way. You have to go step by step to create that. Oxygen pulls electrons down this chain. That's why you need oxygen in your body. Otherwise, you won't be able to transfer or change that NADH into energy. Oxygen needs to do that. And this energy is used to make ATP. Okay? So you have this explosive thing, we could have a lot of energy from here, but that's really not how the electron transport chain works. It's uncontrolled. Bam, you know, it's just, it just, all this energy just happens, but it's not controlled. You may lose a lot of energy. So in electron transport chain, you're going to have to do it in steps, which is more controlled, and we won't lose any of those electrons. It's more controlled. Okay? Good stuff?